So proposition 2, I'll draw the diagram. As we were just discussing, it follows largely, well, it follows completely from proposition 1, and it's not really worth spelling out the proof independently. So proposition 2 says if a straight line is cut, I will not write at random. Then the sum of the rectangles contained by the whole yeah, it's a very strange construction in English. I'll unpack it in a moment. And each of the pieces is equal to the square on the whole. Okay, so what this means is the following. So here's the line. So if a straight line is cut, say it's C, the sum of the rectangles contained by the whole straight line in each of the pieces. Okay, so what that's referring to is, oh, and I've drawn this too long. Forgive me. So remember from last time that the rectangle contained by two lines means the rectangle formed by placing those two lines at right angles. So each of the pieces, there are two pieces here. There is the piece AC and there is the piece CB. And I can construct a rectangle on each of those two pieces contained by each of those pieces separately and the whole, which is AB. Right? So I can make a line here that's as long as AB and a line here that's as long as AB and construct these rectangles. And it's saying the sum of those two is the square on AB. So algebraically, if I were to represent this by C, B, and this length by A, what it's saying is that AB plus AC is equal to the square of A, and A here is B plus C. Okay, so let me draw that in the picture. So what we do is we take a line of the same length as AB, we construct a square on AB, we recall the proposition that does that last time, then we draw a line, let me just call this D. We draw a line through C parallel to AD. That gives us these two rectangles. They add up to the whole. And the whole is the square on AB. So that's the proof of the proposition. I mean, that's enough of a sketch. It's the same idea as proposition 1 and indeed follows directly from it. So maybe we'll leave it at that and move on to proposition 3 unless you have some comment about that one, Kenneth. I can't hear you if you did have a comment, Ken.
I'm not saying anything. I just
okay. Okay, you want to do proposition 3?
Cool. Do I have to steal the all from you?
Yes, go ahead.
Cool. So proposition 3 here is very similar to 1 and 2, and the construction and proof follows. So I'll give the statement and just briefly indicate how the reasoning is done for the proof. So proposition 2.3, if a straight line, I'm going to say AB, is cut at C. Okay, so I'll also do the diagram here as well. Oh, that's not good. Straight line. A straight line, right? So I'm going to have AB. And I want to have a point at C here. then the rectangle contained by AB and BC So remember, this is Euclid's way of saying a rectangle with one side equal to AB and the adjacent side equal to BC. AB and BC is equal to the rectangle, or maybe I'll say to the sum of the rectangle contained by A, B, and AC and BC and the square on BC. So let's draw these in. So we've got AB, and you want a rectangle contained by AB and BC, so we're going to construct a square here on BC. So there was a proposition 46, 1.46 that allows us to construct this square. So this is a square, right? So this is proposition 1.46, right? Gives us the square here, gives square on BC. And then we, similarly, as we did before, construct a parallel line from A that's parallel to, I guess I should name these points, D, right? So we're going to have a line through A parallel to DC, I guess intersecting DC at F. And so this follows from proposition 31, 1.31, right? And so, so I guess the statement here really is that the sum of the parts is equal to the whole, right? So the rectangle bounded by or contained by AB and BC is this big one here, right? And that the square on BC is this one here. And the rectangle contained by AC and BC is this one here. And, you have to do some basic reasoning to show that this is the sides are indeed opposite sides of these are indeed the same, and there you have it. And this is really a special case of one, because the algebraic version of this is A plus B times A equals to A squared plus AB, and I guess you're kind of calling this distance here A and this distance here B, right? And so if you recall, the identity from proposition 1 was more general, right? It was A plus B plus C plus dot dot dot, times. I'll put an X there. I know I didn't use X. Probably used an A there. This is XA plus XB plus XC plus, right? So that was proposition 1, and here we have a kind of a more specialized version of the same proof, formula, and statement. Okay, so I think that's it for 3.
Is the proof just that we've already proved prop 1?
Yeah, I guess the proof is really, we kind of went through this reasoning before in proposition 1. We cut up the big rectangle into smaller rectangles and said the sum of the parts is equal to the whole. And here, I've almost reproduced the proof in the construction, but I'm, just going to leave it there and say either it follows from 1 or, the proof is really the same, right? The diagram here is almost the proof.
Right. So, why bother with this? I guess if it is just a special case.
Yeah, that's the question that we were discussing. Dan and I were 2 and 3 were very much special cases of A. I guess we're 1. Sorry, I guess we're leaving it in there for completeness, and I guess we're also, not wanting to delete things from Euclid.
Sure, yeah.
Is Dan still there? Oh, yeah, I can't hear. Can everyone else hear Dan? Is it just me? Wait, maybe I should reset.
Oh, I can't hear him either.
Oh, okay. All right. I guess wait, should I attach a speaker? Why am I attaching a speaker? Dan left.
Oh, so he was supposed to respawn over here.
Oh.
He got a G.
You're back. You drove back. Awesome.
It's the water. There should be a bridge there, so you can drive it straight over and land in the middle of this. Jump out of the car and start.
It's funny, I spawned right here.
Yeah, 'cause I think if someone's attached a speaker, they'll spawn immediately.
Oh, that's why you were saying I should. I guess I didn't attach fast enough.
Yeah, that's all right. Okay, so the main event is proposition 4, where something new actually happens. This is going to use a few propositions we haven't seen for a while, so I'm just going to draw some diagrams for those. Propositions 1.46 and 1.31 we've used a few times. Maybe you don't know them off by heart, that's fine, but you recognize the principles. But I think, let's see, proposition 1.29 we haven't seen for a while, so let me just put up the diagram for that. So yeah, that's this one, which we remember. So that says if you have a straight line, that's this guy, EF, falling across two parallel lines, then alternate angles are equal to one another. So this and this, this and this. And the internal angles on the same side are equal to 2 right angles. So okay. And the other one we're going to need is proposition 1.34, which is about parallelograms or parallelogrammic figures, as it says. So that's a diagram that looks like this. And the proposition says the opposite sides and angles are equal to one another. Remember, that's at least the way we define it, not immediate, right? Parallelograms are made up of 2 pairs of parallel lines. So the sides are parallel to one another, but they don't have to actually prove they're equal in size. So their opposite sides and angles are equal to one another. So this is equal to this, and this is equal to this. And diagonals cut them in half. I don't think we're using that part. Maybe I'm wrong. We'll see. Okay, so that's a bit of review. Maybe I'll add to that list as we go through the proof. I'm not sure yet. So book 2, proposition 4. What it says is if a straight line is cut, and the square on the whole is equal to the sum of the squares on the pieces and twice, hopefully you know the algebraic identity already, and twice the rectangle contained by the pieces. What's the identity?
a plus b squared equals a squared plus 2ab plus b squared.
Yeah, right. Okay, so here's our line, AB. And we're going to cut it here at C. And then we're going to take a square on AB. And the claim is that if we were to, I'm already into the construction, I guess. So we'll just start and then, let me see, is this going to take me to the next board set? Yeah, that's unfortunate. I'll probably just erase the review stuff on the left-hand side in a moment. Okay, so let's perform some constructions. So I'm going to construct a square on, so I'll give some names to these vertices. So this is D, and this is E. Okay. So forgive me for doing this around a funny way, but the next board is not going to fit both in the same screen. So proof. Construct a square on AB. Okay, so that's ADEB, and that's proposition 1.46. So I've already indicated that. Join BD and let CF be drawn through C parallel to AD. It's prop 1.31. So I'll fill that in. So this is F. It's not very straight. Yep. And let HK have been drawn through G. Wait, oh, I needed to connect B to D, right? And then this point is called G. Draw a line parallel through G parallel to AB. That's HK. Again, by proposition 3.1. So similarly, draw HK through G. Oh, I didn't join BD through G. The G is the intersection of BD with CF. I won't write it down, but it's parallel to AB. Okay. So now we apply proposition 1.29. CGB is equal to ADB. Let's just go back to the diagram for a second. CGB is here, is equal to ADB, right, which is here. Okay, and you can see these are the two lines, and this is the line that goes through them. Okay. But ADB is equal to ABD since BA is equal to AD. And this is one of the very first propositions, right? So this is 1.5. So the observation is that this is further equal to ABD, which is here, because BA is equal to AD by construction, and that's in, so that's an isosceles triangle, and the angles at the base are equal. thus CGB is equal to GBC. Why is that? Because CGB, well, yeah, that's the transitivity of equality. All right. So BC is equal to AD. This is again proposition 1.5. It says that in isosceles triangles, the sides subtended by the two equal angles at the base are equal. Right? So sorry, wait. So BC is equal to CG. Yeah. Since CB is equal to GK, why do we know that actually? CB and GK. I think that's the proposition about parallelograms again, right? So we know that the sides CB and GK are parallel by construction. CG is parallel to BK by construction. So that's a parallelogram, and opposite sides of a parallelogram are equal. So I think that's, it's not, there's no citation of 1.29 there, but I think that's, was it 1.34? I forgot. 1.34. But I think that's another instance of that. Okay. And CG to KB. Have a look at the diagram. CG to KB. Yeah, same reason. Oh, it actually does cite. I apologize. It does cite 1.34. Thus, GK is also equal to KB. GK equals KB. Agreed. Thus, CGKB is equilateral. I guess we're not saying it's a square yet, right? But it does have all sides equal. So I say that it is also right-angled. Since CG is parallel to BK, why? Yeah, by construction. And the straight line CB is fallen across them. Yes. The angles KBC and GCB are thus equal to two right angles. Right. So KBC plus GCB equals two right angles. That's what I just reminded you of. That's 1.29. But KBC is a right angle. Right, by construction. Yeah. So I guess this is what we talked about at some point. Thus, BCG is a right angle. It's like a little, there's an idea about subtraction there we discussed back in the first season. So this is justified. Okay. So the opposite angles are also right angles. Yeah, I'll just say so all of the angles are right. So this is again 1.34. Okay, so thus it's equilateral. It's let me move to the next. Let me try and do it underneath this one. I apologize for the bad formatting. Oh, somebody's in the orb cam. Ken, I think it's you. Can you step back a second? There you go. Okay, so we've proven that this CGKB is equilateral and all angles are right. So hence CGKB is a square. And it is on CB. Just applying the same reasoning, HF is also a square. The rest is just blather, as far as I can tell, right? So we're done, I think. So I'll just say it out loud rather than write it all. So we've now constructed inside the square on AB two squares, HF and CK. HF is a square on, well, HG, which is equal to AC, because those are opposite sides of a parallelogram. So HF is a square on AC, and CK is a square on CB. And then we just compare GK, that's equal to CB. GF is equal to HD, which is equal to HG, which is equal to AC, etc. And we'll see that the original statement is true because these guys fit inside the larger square. So hence, we have shown the square on AB decomposes as claimed. QED. Yeah, I really quite enjoyed that one.
Yeah, that was cool.
How are we going for time? Yeah, I guess we can probably not do any more formally. We can chat about this one if we want. I don't know what's in proposition 5.
Yeah, I have, oh, that's the Neumann one.
Oh, right,
Right.
there's 2. Yeah. Yeah, I find it. I find these. I mean, I guess this is a familiar. I would even use this to explain expanding the brackets if I were to explain this formula to a primary school child. So I suppose this demonstration is it's not unfamiliar, but I wonder if there's any. I mean, I wonder if there's any derivations of algebraic identities in book 2 that we'll actually find surprising. Like maybe there's like the binomial formula or something more generally than this. I mean, I don't know how. I mean, of course, you could do a plus b to the power 10, right? But it wouldn't be in book 2 because it's not going to fit into the plane.
Yeah.